Hello, everybody. Welcome back. We are going to start with a little bit of a review. We've covered some pretty sophisticated concepts, maybe not things that you've been thinking carefully about in your pasts. And so it's a worthwhile thing for us to do, just go over them and make sure that you understand them completely before moving forward. And when we do move forward, we're going to be getting into some pretty fancy stuff. And it's going to come out to be something that is really cool and interesting. So there's something that we have in mind at the end. By the time we get to the end, we'll be fully enthused about all of this again, right? So first, exergonic, exo, kind of thinking out, endo meaning in. Basically, endergonic reactions are the ones where energy is going in. Exergonic reactions are the ones that are where energy is coming out, right? Now, what this amounts to in our context is that anytime we talk about any type of endergonic reaction or endergonic process, it requires there to be an outside source of energy to provide the energy required to drive the system to a higher energy state, which basically is what we mean when we say a reaction is endergonic, right? This is all reviewed, this is all covered in the chapter that you read for the last lecture and also that we discussed in the last lecture. Now, as we know, we have examples of this. Chemical reactions. Chemical reactions are ones where you rearrange the covalent bonds, and so you end up with products that are different from the reactants. And so we have on one hand side of the reaction, reactants. This is a chemical reaction. At the end of the reaction, we have products. Okay. Now, to determine exergonic versus endergonic, all we're really doing is asking whether the chemical energy potential of the reactants, whether the reactants are at a higher or lower energy state relative to the products. In other words, if we actually think of this as a hill, are the products at a higher energy state? Are we basically pushing the reactants uphill, up the energy hill, or are the products at a lower energy state? And so the reactants are kind of like moving downhill, right? And so similar to moving a car along the road, if the car is being pushed uphill, that requires energy to go in. As the car is rolling downhill, we don't even need to turn the motor on. We can have the car move from point A to point B without there being any energy input. And so, yeah, it really does boil down to, in a chemical reaction, whether the energy is higher at the product side or whether it's lower at the product side. Right? If the products represent a lower energy state, exergonic. If the products represent a higher energy state, endergonic. Right? And so if you have two things like glucose and starch, okay? Good example. Starch is a polysaccharide. Glucose is a monosaccharide. But you know that going this direction, this is dehydration synthesis. Going in the other direction, we would call it hydrolysis. Okay. And so at this point, you note that dehydration synthesis, this is the reaction that requires energy to go in. So this must be the uphill reaction, right? Hydrolysis is a downhill reaction. So really, if you wanted to draw this uphill reaction, glucose represents a lower energy state compared to starch. Starch represents a higher energy state relative to glucose. And therefore, when we hydrolyze starch, it would be a downhill reaction. Now, which is the one that requires ATP energy? Well, it's the uphill one. Okay. Uphill reaction, anabolism, dehydration synthesis, work, right? The opposite reaction, they're going downhill. The opposite reaction that's going downhill, hydrolysis, catabolism, non-work. Okay? What this means is that for anybody that says it's hard work digesting the meal that I just ate, technically you could say that's not true because the actual digestion of your food, hydrolysis of proteins into amino acids, hydrolysis of starches into monosaccharides and disaccharides, hydrolysis of fats into fatty acids and glycerol. The actual digestion, the hydrolysis part, they're all examples of non-work. Right? You can use that at your next big meal aftermath. Okay, note for no charge. Next example. So we've done that, right? Transport, translocation of stuff. And we know that if we have a high concentration of glucose on one side, low concentration on the other side, okay? If the glucose molecules are moving from left to right, basically towards a lower concentration, we're moving towards an equilibrium, and therefore that would be a downhill reaction. DH, or downhill reaction. On the other hand, if we took glucose from the low concentration side and moved it over to where the concentration of glucose is higher, that's not something that we expect to happen spontaneously because of the natural forces of the universe. That has to be driven with an outside source of energy, and that would be an uphill reaction. And that would be an example of work, right? And yeah, when it goes in this direction, change colors again craftily. When it goes in this direction, we would call this active transport. We know that ATP energies are required to happen in that direction. So yeah, I'm going from low concentration to high concentration. That would be kind of like an uphill reaction. Arrow going down upwards, and go from a high concentration to low concentration. That would be an arrow that goes downward. We would call that diffusion. Whether it's facilitated diffusion or simple diffusion, there's no energy required to move a solute from where it's abundant to where it's relatively rare. Right? And you could do the same thing for mechanical work. You could say, well, what does it take? What is the amount of work that it takes for you to get up from the floor? You're on the floor, and now you're standing up. Okay? You're basically going from a state way down there to a state that's upwards, and so you might expect that to be an uphill reaction. If you're standing up, you could be completely inert. It doesn't take energy for you to go from a standing up position to a prostrate position on the floor. Okay, you might want to, it won't be very pretty if you don't put any energy into breaking or fall, but theoretically it does not take any energy for you to fall down. It does take energy for you to get up. And so these, even mechanical processes, mechanical movement, or it can be either work, or it could be non-work. Right? And so my objective here is to get you to think about, well, what constitutes work versus non-work in a scientific sense, right? And so we talked about examples based on translocation of solutes. We talked about mechanical examples. You can come up with your own examples on your own. Which is work? Moving the car uphill or moving a car downhill? Which is work? Pumping water to the top of a water reservoir so that you could have pressurized water, or allowing that water to flow downhill. Okay? These are all valid examples of work versus non-work. Okay. Second thing for us to review is energy. And remember, energy is something that you can't really touch. You can sometimes relate to it in the case of light energy or thermal energy. You can feel thermal energy. You've got sensors that will detect that happening. You can sit out in the sun and you can feel the energy. Okay? Your cells become more active because they're actually heating up, right? And so the energy is not something that is necessarily completely foreign to us, but it is something that you can't really put your finger on and touch. It's not physical matter. Right? And I used this last time to say, well, ATP, even though it's really important for us, even though it's an important source of energy, and we often talk about ATP energy, it's not actually energy, right? What it is a fuel. It's a bit of matter that stores chemical energy, and we use that fuel and convert it into another form of matter. We call that waste. Conversion of food into waste is going to release energy that's going to go into some other process, presumably some form of cellular work. Right? Now, in the textbook, it talks about the difference between kinetic energy and potential energy. You know, kinetic energy is kind of like action, kinesis, action. Potential is kind of like energy that can happen at some point in the future, right? And so thermal energy and light energy, those are both examples of kinetic energy. It's energy that is you know, doing its thing in the present. You feel yourself getting warmed up. You don't have thermal energy that is going to warm you up at some time in the future. Okay? If it did that, then it would be potential energy, but that's not the way that heat works. You can't, you know, go out and bathe in the sun and expect that sun to warm you up when you're when it gets cooler at night, right? And so thermal energy, you know, was our example of kinetic energy. The kind of energy that we're talking about with ATP being a potential energy source, right? ATP getting converted to ADP and phosphate. Okay. That's going to release energy. Okay. And therefore, you'd say the ATP has energy content, and that would be chemical energy. So energy potential is the way that we'd say it. Okay. So using the appropriate lingo, say ATP has energy potential because we could release that energy, which would at that point be some form of kinetic energy, as it gets converted from ATP into ADP plus phosphate. Okay. And so you know, there's more for you to think about in terms of getting your mind solidly around the concepts of what constitutes energy and what doesn't constitute energy. Okay. And finally, and now that we're completely up to date on all these concepts, energy versus fuel, kinetic energy versus thermal energy, we can now start talking about these two buzzwords that buzz concepts, things that you could impress your professors by being able to talk about them. Okay, the first law of thermodynamics is a pretty easy one because if you have your mind around the concept of energy, you'll realize that, well, you know, maybe you'll realize it, or maybe you're still getting comfortable with the concept. But the idea is that energy is something that is kind of hard to think about. But the first law of thermodynamics says that the total amount of energy in the universe is a constant. You can't create energy, nor can you destroy it, right? You can, however, okay, this is the important part, convert energy from one form into another. Right? You can take light energy, okay, from the sun, right? Okay, this light energy coming down onto the earth. You could convert that light energy into chemical energy. Okay, like glucose. And this is exactly what happens in the context of a plant. Okay, so what a plant is doing in growing up and becoming a larger plant is it's taking light energy from the sun. We also have raw materials like carbon dioxide and water, but basically the energy that we end up with in the form of a plant is basically energy that has been stored from the energy that was incident on the Earth's surface when we had a sunny day when the plant was undergoing photosynthesis. Okay, this would be an example of an energy conversion. Right, you might be taking chemical energy, glucose, and O2, using that as the energy reaction, and basically getting mechanical energy for mechanical work. Right? Energy to drive mechanical work, kinetic energy to drive your getting up from the floor, right? In order to get up from the floor, that requires lots of ATP. That ATP is being fueled by the synthesis of food molecules, food. This is what we're talking about, right? And this might be a human. In other words, we have lots of examples of energy being converted from one form to another. But what we don't have is energy being destroyed. Okay? It's not like the energy that's there in food is gone after the glucose gets converted into carbon dioxide and water, right? If the matter is still there at the end, the energy is still there at the end. It's just being realized in the form of mechanical work. But that's not all. And here's the second law part, okay? And this is a part that's a lot more complicated to think about, but it's something that has to be understood if you really want to understand science, okay? And it goes like this, right? Yes, you can convert energy from one form into another. You can go from point A, where you've got energy, point B, where you've got energy in a different form. But one thing that's going to happen is that the total, we know that the total amount of energy has to be the same, right? Before and after. But one thing that must increase is this thing called entropy. Okay? Entropy is the, in loose terms, the disorderliness. Okay? The amount of chaos that's there in the energy. In other words, energy comes in many forms. You've got orderly energy, ordered. You've got disorderly energy. Orderly energy would include chemical energy. It would include light energy. Disorderly energy would include largely heat, right? And what I'm saying here is that if we've got an orderly energy form over on the left-hand side and an orderly energy form on the right-hand side, that's not going to satisfy the second law. Second law of thermodynamics says that the overall amount of energy, the overall amount of entropy must increase. And therefore, in order to satisfy this all-critical law of the universe, we have to include the production of heat. Okay. If we're going to be converting food molecules, the energies toward the chemical energy form we have over here, into an orderly form of energy that's useful over here, mechanical work, that on its own is not likely going to satisfy the second law, and therefore the end result must include the production of some heat. Right? Heat is always going to be there when we convert one form of chemical of energy into another form of energy. Yes, we can convert one to the other, but in order to satisfy the second law, we must have some heat produced. Okay. And finally, we get to brown fat. But before we get to brown fat, I'm going to move over to one more slide. And this is one that's, because we're kind of skipping over a bunch of content. We're going from chapter 5, section 10 to chapter 6, section 12. And in between, there's a whole bunch of stuff that we'll be getting to. I mean, we'll be talking about in the coming lectures. But I think that if we're going to be discussing energy and thermodynamic laws, 6.12 is a really great place to end up. Okay, but it has to deal with this. Okay, so if you're going to be converting chemical energy into chemical energy, in other words, if you're going to be using chemical energy on one side of the reaction in the form of like glucose and oxygen. Okay. Glucose and oxygen is the form of chemical energy. Glucose and oxygen are going to be converted into CO2, carbon dioxide, and water. Okay. But the chemical energy that we have in the form of glucose and oxygen at the beginning is going to be converted into, and this is a process he's talking about, chemical energy in the form of ATP. Right? Here's the chemical energy that we're ending up with. And yeah, eventually we'll be using ATP to produce ADP and phosphate, and the energy released is going to be used to drive cellular work. Okay? If this is the reaction that's going on in metabolism, in our metabolism of food, okay, we know at this point that we have orderly energy on the left, orderly energy on the right, and consequently we have to also have heat produced. Okay. Now, as it turns out, in order for, again, we have to have heat produced in order to satisfy the second law. In the overall breakdown of things, the amount of heat produced is about 34% of all the energy that's there on the right-hand side. If we have 100%, we have to account for 100% of the chemical energy that's released when we convert glucose into carbon dioxide. Now, 34% is going to be in the heat, and chemical energy here is going to represent about 66%. And that's actually a very, very high recovery rate. Usually the amount of heat produced is greater. This is actually highly efficient. The more heat you produce, the less efficient you are. And so, while this might sound like a lot of loss, this is actually pretty highly efficient. Okay. Now, on purely theoretical grounds, let's say that we were somehow able to, we somehow manipulated the system so that we still consume 100%, we still consume all the glucose and oxygen, but we reduce the amount of chemical energy, we reduce the amount of ATP energy that we're producing, maybe down to 30%. Okay. In other words, if we reduce the efficiency of our conversion of food molecules into ATP energy, such that we're only ending up with 30% of the chemical energy recovered in the form of ATP, okay, how must that affect the amount of heat produced? Okay. Now remember, first law of thermodynamics says that we have to have the same amount of energy before and after. So in the same way that we were accounting for 66% plus 34%, combining to account for all 100% of the energy that we had at the beginning, we still have to do that. In other words, the amount of heat that has to be produced, it has to be 70% of all the energy that went into the process. In other words, heat production is going to be increasing. All right. Now we can go over to chapter 6, section 12. I think it fits really a whole lot more nicely with what we just talked about than what's going on in actually chapter 6, and that's what we're doing it now, okay? Because we've got this organ that it's fat. It's just like any other organ that's being capable of doing stuff. Brown fat, right? Not your regular yellow, creamy colored fat, the one that causes insulation, the one that makes us, the one that we put on when we reach the age of 40, and the one that we tend to increase in abundance in our bodies after we have a large meal in the holidays, and that's normal yellow fat. Okay? Brown fat is kind of special, right? And so if you read through this, it actually gives you a lot more detail that relies on your understanding of what's going on in chapter 6. So basically, brown fat is doing this thing such that we use all the energy, we eat We eat the same amount of food. That would normally be used to produce X amount of ATP. We have to eat the food, we have to breathe the oxygen, and so, but we would normally produce X amount of ATP, but we're kind of short-circuiting the ATP production, so we end up with less ATP. Right? Not that, in other words, what we basically are doing is making it a mechanism that's less efficient relative to what we normally have in the rest of our cells. Brown fat cells basically have faulty mitochondria. Okay? We discussed earlier how mitochondria are the sites of ATP production. If you make mitochondria but don't set it up exactly right, you could have mitochondria that are consuming all the food molecules but not producing the ATP. And that's easy enough to understand. I mean, there are more efficient machines and less efficient machines, right? But if we produce less ATP, what also must happen? Right. We must produce more of the alternative form of energy, which is going to be heat. Okay. In other words, we're not talking about the same kind of fat that is pretty inactive. It's not terribly, it doesn't do a whole lot. It's not like muscle, it's not moving you around. It's, you know, your usual yellow fat is just storing tissue, storing energy-rich tissue that you might be able to use later if you ever need the calories, right? Okay. But this brown fat is different. The brown fat is equipped with a lot more hemoglobin-like molecules to have it capture more oxygen. It's taking in the same amount of food. In this case, it's actually generating some heat. It's like warm patches of tissue in your body. Okay, is that cool? Now, usually we associate brown fat with babies, the young mammals. Mammals in particular are the kinds of animals that have brown fat. The young mammals tend to be more susceptible to hypothermia, right? To getting too cold, because they're small, they have a larger surface area to volume ratio, so they lose heat more effectively, more quickly. They also tend to have less fat of their own and less fur, right? Mammal babies tend to be born kind of naked. And so while a mammal baby is going to be kind of at risk of hypothermia because of its size and its lack of fur, one thing that's not lacking is nutrition, access to nutrition, because mammals are nursing from mama. In other words, mammals have access to lots of food. They can breathe because there's plenty of oxygen in the air that they're breathing. And so baby mammals are using brown fat to compensate for the fact that they're losing heat because of their small size and lack of body fur. Right? Is that cool? Okay. All mammals do this, with the exception, weirdly, of pigs. Pigs, for some reason, lost through evolution their ability to generate heat using brown fat. Okay. Now what this chapter is doing, it's kind of planting a seed of interest to you, because normally we think of brown fat as something that disappears once you reach a certain age. Once you become large enough, you really don't need the brown fat to compensate for heat loss. Right? You've got a lower surface area to volume ratio, et cetera, et cetera. On the other hand, if you're like me and you really like to eat, it would be cool. I mean, it would be completely awesome if you could turn on your brown fat. It would simply burn off the calories, the excess calories that you consume in that last time you binged on ice cream, or something like that. Whatever your favorite binge food is, rich in calories, if you could turn on your brown fat, you could eat all those calories without gaining a single gram. Okay. Wouldn't it be cool to activate that? I've always thought so, right? And so this whole section in chapter 6, section 12, is addressing that exact issue. But when you think about it long enough, it really does come back to our discussion about the second law, right? We're not generating ATP, we're generating heat instead, right? We're seeing both the first law, we have to account for all 100% of the energy that's there. You can do it either by having 66% come out in the form of ATP energy and 34% as heat, or 30% as ATP energy and 70% as heat. And by doing the latter, we're actually creating a tissue that's able to generate heat for the body. Okay, that's it. Next time we talk more about metabolism and we get more into those things like what are mitochondria and how do they generate the ATP energy that you really need to generate lots of. Okay, bye.